The first humans to reach Uranus will never come back. Not because they'll choose to stay, not because of some catastrophic equipment failure, but because the physics, the biology, and the sheer mathematics of such a journey make a return trip fundamentally impossible with any technology we currently have or will likely develop in the foreseeable future. This isn't speculation. It's written into the brutal arithmetic of deep space travel. Uranus sits 1.8 billion miles from the Sun. To put that in perspective, it's 19 times farther from the Sun than Earth. When Voyager 2 made its historic flyby in 1986, it had been traveling for 9 years and covered over 1.8 billion miles just to get there. 9 years of continuous flight through the void. And Voyager 2 was moving fast, using gravity assists from Jupiter and Saturn to build speed. It never slowed down. It just kept going, hurtling past Uranus at thousands of miles per hour, snapping photos as it flew by. A human mission couldn't do that. You can't just fly past your destination when you're carrying people. You need to slow down, enter orbit, conduct your mission, then somehow accelerate back toward Earth. Each of those steps requires fuel, enormous amounts of fuel. If you find comfort in these gentle explorations of space and science, I'd be grateful if you'd consider subscribing and giving this video a like. Here's where the math becomes your enemy. There's something called the rocket equation, formulated by a Russian scientist named Konstantin Tsiolkovsky over a century ago. It's elegant, it's simple, and it's absolutely merciless. The equation tells us that the amount of fuel you need grows exponentially with the distance you want to travel and the speed you want to achieve. Think about driving from New York to California and back. Now imagine there are no gas stations along the way. None. You'd need to carry all your fuel with you from the start. But here's the problem. Fuel has weight. The more fuel you carry, the heavier your vehicle becomes. A heavier vehicle needs more fuel to move. So you need to carry even more fuel to move the extra fuel, which makes you heavier still, which requires more fuel. The cycle feeds on itself. In space, this problem becomes catastrophic. If you wanted to travel to Uranus and back, you'd need fuel to accelerate toward Uranus, fuel to slow down when you arrive, fuel to leave Uranus, and fuel to slow down when you return to Earth. Each stage multiplies the fuel requirement of every stage before it. Current estimates suggest that even with the most optimistic propulsion technology we have, a one-way trip to Uranus would take at least 13 years. That's using a Falcon Heavy rocket with a gravity assist from Jupiter. 13 years just to get there. The return trip would take similar time, assuming you could even carry enough fuel to make the journey back. But let's say we solved the fuel problem somehow. Let's say we developed nuclear thermal propulsion, which uses a nuclear reactor to superheat hydrogen and expel it at tremendous speeds. This technology exists in theory and offers about twice the efficiency of conventional chemical rockets. Even with this advancement, you're still looking at years of travel time each way. The human body wasn't designed for decades in space. Every single day beyond Earth's protective magnetic field, cosmic radiation tears through your cells. These aren't the relatively gentle rays from the sun. This is galactic cosmic radiation, particles accelerated to near light speed by supernovae and other violent cosmic events. They pass through spacecraft hulls like they're not even there. NASA has identified 4 primary radiation risks for deep space missions: cancer, degenerative tissue damage, central nervous system effects, and acute radiation syndrome. Studies on mice exposed to the type of low-dose, chronic radiation astronauts would face on a mission to Uranus showed devastating results. The radiation impaired cellular signaling in the hippocampus and prefrontal cortex. Memory formation broke down. Anxiety spiked. Researchers predicted that 1 in every 5 astronauts would develop anxiety disorders, and 1 in every 3 would experience significant memory impairment. Now scale that up from a few months to multiple decades. You're not just risking cancer anymore. You're virtually guaranteeing it. You're watching your brain slowly deteriorate. Your bones weaken from lack of gravity. Your muscles atrophy. Your cardiovascular system adapts to 0G in ways that make returning to gravity potentially fatal. And we haven't even talked about what happens when you reach Uranus itself. The planet is cold. Not just winter coat cold. Not even Antarctic cold. Uranus holds the record as the coldest planet in our solar system, with atmospheric temperatures dropping to -371 degrees Fahrenheit. That's 224 degrees below 0 Celsius. At those temperatures, ordinary materials become brittle and shatter. Metals contract. Seals fail. Nothing we've built was designed to operate in such extreme cold for extended periods. The wind screams across the planet at 560 miles per hour. Hurricane-force winds on Earth reach maybe 150 miles per hour. These winds are nearly 4 times stronger, tearing through an atmosphere of hydrogen, helium, and methane. There's no solid surface to land on. The planet is a gas giant, or more accurately, an ice giant. What we call the surface is just an arbitrary point where atmospheric pressure reaches 1 bar, the same as Earth's sea level pressure. Below that, the atmosphere just gets denser and denser, gradually transitioning into a liquid mantle of water, methane, and ammonia ices surrounding a rocky core. You can't land there. You can't walk on it. You can't build a base. Any mission to Uranus would involve orbiting the planet, studying it from a distance, perhaps sending probes into the atmosphere. But you couldn't establish any kind of permanent presence. The radiation environment around Uranus presents another nightmare. When Voyager 2 flew past in 1986, it detected intense electron radiation belts, second only to Jupiter's in ferocity. Scientists still don't fully understand how these radiation belts formed or why they persist. The planet's magnetic field is bizarre, tilted nearly 60 degrees from its rotational axis, and offset from the planet's center by 1/3 of its radius. This creates a chaotic, tumbling magnetosphere that would batter any spacecraft with unpredictable bursts of radiation. Recent research suggests Voyager 2 might have observed Uranus during an unusual compressed state of its magnetosphere, present less than 5% of the time. Under normal conditions, the radiation environment could be even more hostile than we currently believe. Communication from Uranus would test the limits of patience. Light takes 2 hours and 40 minutes to travel from the Sun to Uranus. Radio signals, traveling at the same speed, would face identical delays. Ask a question from Uranus, and you'd wait over 5 hours for a response from Earth. 2.5 hours for your signal to reach home, 2.5 hours for the answer to come back. In an emergency, you'd be completely alone. Equipment failure, you'd have to solve it yourself. Medical crisis, Earth's doctors could only watch helplessly as events unfolded in slow motion, their advice arriving hours too late. The psychological weight of that isolation would be crushing. Astronauts on the International Space Station can look out the window and see Earth. They know that in an emergency, they could be home in hours. Mars missions would push that to months. But Uranus, you'd watch Earth shrink to an insignificant blue dot, then fade into the background stars. For years, you'd see nothing but the black void and distant points of light. Studies of astronauts in low Earth orbit already show concerning psychological effects. NASA found that 23% of male astronauts and 85% of female astronauts showed symptoms of anxiety. Depression affected 35% of male astronauts and 43% of female astronauts. That's in the relatively safe environment of low Earth orbit, with Earth constantly visible, with rapid communication, with the knowledge that rescue is possible. One cosmonaut, Valentin Lebedev, struggled with depression after only 7 months in space. A round trip to Mars would take roughly 18 months. Researchers openly acknowledge that the psychological risks for such missions are severe. For Uranus, multiply those risks by a factor of 10 or 20. You're looking at decades in a confined metal tube with no hope of rescue, no new faces, no fresh air, no sunlight, no horizon. The human mind wasn't built for that. We evolved in wide open spaces, with changing seasons, with communities, with the ability to walk away from stressful situations. Lock someone in a small room with the same handful of people for 20 or 30 years, and psychological breakdown isn't a risk, it's a certainty. Then there's the question of supplies. Each crew member needs about 11 pounds of food, water and oxygen per day. They produce a similar amount of waste. On a 10-year journey, that's 40,000 pounds of supplies per person. For a crew of 6, you're looking at 240,000 pounds of consumables. And that's just one way. Even with the most advanced recycling systems, you can't achieve perfect efficiency. Water recycling on the ISS recovers about 93% of water from urine and condensation. That missing 7% adds up over years. Air recycling faces similar limitations. Some loss is inevitable. For a mission to Uranus, you'd need to carry decades worth of supplies or develop closed-loop life support systems far beyond anything we've created. We're talking about systems that can operate flawlessly for 20, 30, even 40 years without resupply, without major repairs, without failure. No such system exists. The ISS requires regular resupply missions. It requires constant maintenance. Pumps fail, filters clog, electronics degrade. On the ISS, replacement parts arrive every few months. On a ship to Uranus, whatever you launch with is all you'll ever have. But let's say we somehow solved all of these problems. Let's say we developed revolutionary propulsion that cut travel time in half. Let's say we created perfect radiation shielding. Let's say we built life support systems that could run for decades without failure. Let's say we selected crew members with superhuman psychological resilience. You'd still face the fundamental problem that makes the title of this video absolute truth. The fuel requirements for a return journey are so staggering that no conceivable rocket could carry enough. To slow down at Uranus, you need fuel. To leave Uranus, you need even more fuel. To slow down when you return to Earth, you need fuel you've been carrying since you left. Every kilogram of fuel for the return journey is a kilogram you had to accelerate all the way to Uranus, which required additional fuel, which required more fuel to lift that fuel. The mathematics spiral into impossibility. Engineers have run the numbers countless times, using every propulsion technology we have or can reasonably imagine developing. The answer keeps coming back the same. A one-way trip to Uranus is theoretically possible. Difficult, dangerous, pushing the absolute limits of human endurance, but possible. A round trip with current or near-future technology isn't just hard. It's not just improbable, it's functionally impossible. The mass ratios don't work. The fuel requirements exceed what any rocket could carry. The time requirements exceed what any human could survive. This is why the first humans to reach Uranus will never come back. Not unless they're willing to die there. Understanding why requires looking at something most people never consider. The rocket equation. It's a mathematical truth discovered by Konstantin Tsiolkovsky in 1897, and it's the reason interplanetary travel is so brutally difficult. The equation itself is deceptively simple. Delta V equals exhaust velocity times the natural logarithm of initial mass divided by final mass. What that means in practical terms is devastating. Every kilogram of payload requires exponentially more fuel. Want to go twice as fast? You don't need twice the fuel. You need 4 times the fuel. Want to carry fuel for a return journey? You need fuel to accelerate that return fuel, which requires more fuel to accelerate the fuel that accelerates the fuel. It spirals into absurdity quickly. Here's a thought experiment. Imagine you're planning a road trip from New York to Los Angeles and back. Simple enough. Fill your tank, maybe stop for gas once or twice, drive home. Now imagine there are no gas stations. Anywhere. You have to carry all the fuel you'll need for the entire round trip before you leave your driveway. Suddenly you need a tanker truck worth of fuel. But your car can't pull a tanker truck, so you need a bigger engine, which needs more fuel, which requires an even bigger engine. The problem compounds until you're trying to move a vehicle the size of an office building. That's the rocket equation in action. And it's why Voyager 2, which visited Uranus in 1986, has been coasting through space for nearly 50 years. It fired its engines to leave Earth, used gravity assists from Jupiter and Saturn to pick up speed, and has been drifting ever since. No fuel for slowing down. No fuel for course corrections beyond tiny adjustments. Certainly no fuel for coming back. For a human mission, you can't just coast past Uranus and wave as you fly by at 40,000 miles per hour. You need to slow down, enter orbit, spend time there, then leave. Each of those maneuvers requires fuel, enormous amounts of it. Let's run some numbers. A conventional chemical rocket like those we use today has a specific impulse around 450 seconds. That's a measure of efficiency. How much thrust you get per unit of propellant. To reach Uranus in reasonable time, you need a delta V budget of roughly 30 kilometers per second. Just to get there, slowing down into orbit around Uranus. Another 15 kilometers per second, leaving Uranus to return to Earth. Another 15. Slowing down to Earth orbit instead of burning up in the atmosphere. Another 10. That's 70 kilometers per second of total delta V. With a specific impulse of 450 seconds, the mass ratio required is astronomical. For every kilogram of spacecraft that returns to Earth, you'd need to launch roughly 200,000 kilograms from Earth orbit. A crew module that weighs 10,000 kilograms. You're talking about launching 2 billion kilograms. That's 2 million metric tons. The entire International Space Station weighs 420 metric tons. You'd need to launch something 5,000 times more massive. It doesn't work. The numbers don't allow it. This is why NASA and other space agencies focus on more efficient propulsion technologies for deep space missions. Nuclear thermal propulsion is one option. Instead of chemical combustion, you use a nuclear reactor to superheat hydrogen propellant before expelling it through a nozzle. This roughly doubles your specific impulse to around 900 seconds. Better, but still not good enough. Even with nuclear thermal propulsion, the mass ratios for a Uranus round trip remain prohibitive. You'd still need to launch thousands of tons to return a small crew capsule. Ion drives offer even higher efficiency. Some designs achieve specific impulses of 10,000 seconds or more. The problem: thrust. Ion drives produce incredibly weak thrust. The Dawn spacecraft, which used ion propulsion to visit Vesta and Ceres, had a maximum thrust of 90 millinewtons. That's about the weight of a single AA battery. For accelerating a massive crewed spacecraft over reasonable timeframes, ion drives simply can't provide enough push. You'd spend decades accelerating, decades decelerating. The mission duration stretches beyond human lifespan. What about refueling at Uranus? Manufacturing propellant from local resources? Interesting idea. Except Uranus doesn't have a solid surface to land on. It's a gas giant. Well, technically an ice giant, but the principle holds. The visible surface is just the top of an atmosphere that extends thousands of miles down, gradually becoming denser and hotter until you reach a possible rocky core under millions of atmospheres of pressure. You can't land there. You can't mine there. There's no there to work with. The moons then? Uranus has 27 known moons. Surely one of them could provide resources. The largest, Titania, has a diameter of just under 1,000 miles. It's mostly water ice and rock. Could you extract hydrogen and oxygen from the ice? Technically, yes. But you'd need to bring equipment to mine it, process it, liquefy it, and store it. That equipment has mass, which requires fuel to transport. Which brings us back to the rocket equation. Even if you could manufacture propellant at Uranus, you'd still need enough fuel to slow down when you arrived. You can't aerobrake in Uranus's atmosphere without specialized heat shields, and even then, the gravity well is deep enough that you'd need additional propulsion to avoid falling in permanently. The numbers keep failing. Some proposals suggest nuclear pulse propulsion, detonating small nuclear bombs behind a massive pusher plate to generate thrust. This could theoretically achieve the velocities needed. The Orion project in the 1960s explored this concept. Setting aside the political and environmental nightmare of launching thousands of nuclear warheads into space, the engineering challenges are staggering. The pusher plate would need to withstand repeated nuclear detonations. The shock absorbers would need to protect the crew from accelerations that would otherwise liquefy human organs. The radiation shielding would need to be absolute. And you'd still face the fundamental problem. Every nuclear bomb you bring for the return journey is mass you have to accelerate to Uranus, which requires more bombs to accelerate those bombs. The rocket equation is inescapable. What if we didn't bring fuel at all? What if we use solar sails? Light exerts pressure. Tiny but real. A large enough sail could accelerate a spacecraft without propellant. Except at Uranus's distance, sunlight is 1/400th as intense as at Earth. A solar sail that might work in the inner solar system becomes nearly useless. You'd need a sail hundreds of miles across to generate meaningful thrust. The mass of the sail itself becomes prohibitive. Laser propulsion from Earth beam enormous amounts of energy to push a sail-equipped spacecraft. We don't have lasers powerful enough. Even if we did, focusing a beam across billions of miles introduces impossible targeting challenges. Every solution leads to the same conclusion. The energy requirements for a round trip exceed what any feasible propulsion system can provide. But let's imagine we somehow solved propulsion. Let's say someone invents a miracle engine tomorrow that somehow bypasses the rocket equation. Antimatter drives, zero-point energy, something that gives us unlimited delta V for minimal mass. You'd still have a different problem that makes the title true. Time. Even with revolutionary propulsion that cuts travel time to the absolute minimum physics allows, you're looking at years in transit each way. The speed of light is the ultimate speed limit. Nothing with mass can reach it. Even if you could accelerate to some significant fraction of light speed, say 10%, you'd still need over 26 years to reach Uranus, plus deceleration time, plus the return journey. You might say that's fine. Astronauts could spend 26 years traveling. But 10% light speed requires energy inputs that dwarf anything humanity can currently generate. The kinetic energy of a spacecraft moving at that velocity is measured in exajoules. That's millions of times more energy than the largest nuclear weapons ever built. More realistic velocities make the timeline worse. Voyager 2 took 9 years to reach Uranus, traveling at roughly 35,000 miles per hour. It was going so fast it couldn't stop. A crewed mission would need to travel slower to allow for deceleration. Figure 15 years outbound. Another 15 back, 30 years minimum, in a confined spacecraft, with the same handful of people, breathing recycled air, drinking recycled water, eating the same meals prepared from shelf-stable ingredients. No privacy, no escape, no possibility of resupply or rescue. The psychological studies on isolation don't paint an encouraging picture. Research on Antarctic winter rover crews, submarine personnel, and ISS astronauts all show the same patterns. Even with careful screening, even with extensive training, people struggle after months of confinement. The longest continuous spaceflight by a human is 437 days. Valery Polyakov aboard Mir in 1994 to 1995. He trained for years. He was monitored constantly. He had regular communication with Earth. And even then, the isolation took a measurable toll. Multiply that by a factor of 25. 30 years versus 14 months. The psychological strain would be incomprehensible. Depression, anxiety, interpersonal conflicts, cognitive decline. These aren't possibilities, they're certainties over that time frame. NASA researchers studying long-duration spaceflight for Mars missions, which would only last around 2 years, have identified serious concerns. 1 in 5 astronauts would likely experience anxiety disorders. 1 in 3 would face memory impairment, and that's for a mission 15 times shorter than a Uranus round trip. Communication delays compound the isolation. From Uranus, radio signals take over 2.5 hours to reach Earth, another 2.5 hours for a response. A simple conversation becomes an exchange of messages separated by 5-hour gaps. In an emergency, Earth can't help, can't advise, can't do anything except listen to what already happened hours ago. the crew would be entirely on their own for decades. The physiological effects are equally grim. Cosmic radiation accumulates. Bone density decreases despite exercise. Vision deteriorates. The cardiovascular system weakens. Immune function declines. Even on the ISS, with crews rotating every 6 months, astronauts return measurably damaged. Multiply that by 60. That's how many 6-month increments fit into 30 years. No human has ever experienced anything close to that duration in space. We genuinely don't know if survival is possible even with perfect life support. But even if you could somehow keep humans alive and sane for 3 decades in a tin can, you'd still need to solve the fuel problem, because that miracle propulsion system doesn't exist. The rocket equation still applies. The mass ratios still don't work. This is the inescapable truth about Uranus. The distance isn't just far, it's prohibitively far. The energy requirements aren't just high, they're impossible with any technology we have or can reasonably develop. Human missions to Uranus aren't just difficult or dangerous. They're not even in the realm of expensive or technically challenging. They exist beyond the boundary of what physics and human physiology permit, given our current understanding. The first humans to reach Uranus will be making a one-way trip. Not because we lack the vision or courage to bring them back, but because the universe itself has imposed constraints that no amount of engineering can overcome. The fuel doesn't exist. The engines don't exist. The life support systems don't exist. The psychological resilience doesn't exist. Uranus remains untouchable, not because we haven't tried hard enough, but because some destinations are simply too far for creatures evolved on a small planet orbiting a medium star. We're biological beings adapted for Earth's gravity, Earth's atmosphere, Earth's radiation environment. Uranus offers none of that, just cold, distance, and mathematics that refuse to cooperate. Let's talk about radiation, because even if you solved propulsion and life support and psychological endurance, the universe has one more way to kill you. Space beyond Earth's protective magnetic field is hostile, not in a dramatic Hollywood explosion kind of way, in a slow, invisible, cellular destruction kind of way. Radiation in deep space doesn't announce itself, it just accumulates. Day after day, year after year, damaging DNA, destroying cells, breaking down the biological machinery that keeps you alive. Earth's magnetosphere shields us from most cosmic radiation. Step outside that protective bubble, and you're exposed to a constant barrage of high-energy particles, galactic cosmic rays, solar energetic particles, heavy ions traveling at near light speed. Every single day in deep space, a hydrogen ion passes through every cell nucleus in your body. Every few months, heavier particles tear through your tissues. This isn't speculation, it's measured fact. NASA has identified 4 primary radiation risks for deep space missions: cancer, degenerative tissue damage, central nervous system deterioration, acute radiation syndrome. Notice those aren't possibilities, they're identified risks, meaning they will happen given sufficient exposure. The cancer risk alone is staggering. Chronic low-dose radiation exposure increases cancer probability dramatically. But that's almost the least concerning effect, because at least cancer takes time to develop. The cognitive effects start immediately. Research on mice exposed to radiation levels comparable to deep space missions showed measurable brain damage, impaired cellular signaling in the hippocampus, damage to the prefrontal cortex. The result? Learning disabilities, memory impairment. During a deep space mission, researchers predict 1 in 5 astronauts would develop anxiety disorders. 1 in 3 would experience significant memory problems. Think about what that means. You're on a 30-year mission, no possibility of return, and within a few years, you can't remember procedures correctly, can't solve problems as effectively, can't think as clearly. Your brain is literally deteriorating from radiation exposure, and there's nothing you can do about it. The psychological implications compound the direct neurological damage. Imagine knowing your mind is degrading, watching yourself become less capable, less sharp, less you, while trapped in a spacecraft with no escape. For decades, Mars missions, which would last around 18 months, already raise serious concerns about radiation exposure. Researchers acknowledge the cognitive risks are significant, and Mars is comparatively close. The radiation exposure for a Uranus mission would be roughly 20 times greater. Shielding doesn't solve the problem. It helps, but it's not a solution. To block galactic cosmic rays effectively, you'd need meters of material. Lead, water, polyethylene. Doesn't matter. You need mass, lots of it. And remember the rocket equation. Every kilogram of shielding is another kilogram you have to accelerate, decelerate, and accelerate again. The fuel requirements become even more absurd. Some proposals suggest using water as shielding. Surround the habitat with tanks of water that also serve as drinking supply. Clever. Except you'd need so much water to provide meaningful protection that the spacecraft mass becomes prohibitive. And as you consume the water, the shielding degrades. So you're most protected at the beginning of the journey and least protected at the end when you've already accumulated years of exposure. Magnetic shielding has been proposed. Generate a magnetic field around the spacecraft to deflect charged particles. Sounds great. Except the power requirements are enormous. You'd need a nuclear reactor producing constant, substantial power output for 30 years, without failure. And even then, magnetic fields don't stop neutral particles or the highest energy cosmic rays. Here's what makes Uranus particularly dangerous. The radiation belts. When Voyager 2 flew past Uranus in 1986, it detected something unexpected. Intense electron radiation belts, second only to Jupiter's in strength. These belts were so powerful, they puzzled scientists. Uranus doesn't have an obvious plasma source to maintain such intense radiation. Yet, there they are, trapping high-energy particles in the planet's magnetic field. Any spacecraft approaching Uranus would have to pass through these belts. The radiation exposure during that passage would be catastrophic. Even brief exposure to radiation at those intensities can cause acute radiation syndrome, nausea, vomiting, fatigue. That's the mild version. Higher doses cause hemorrhaging, organ failure, death. And here's the twist. Recent research suggests Voyager 2 might have observed Uranus during an unusual period. The solar wind had compressed the magnetosphere into an abnormally small configuration. This state only occurs about 5% of the time. If the spacecraft had arrived a few days earlier, the magnetosphere would have been dramatically different, possibly even more intense. We have one data point, one flyby, one snapshot of Uranus's radiation environment during one specific moment. We don't actually know what conditions are normally like. We're planning missions based on data that might not be representative. The magnetic field itself presents another hazard. Uranus's magnetic axis is tilted nearly 60 degrees from its rotation axis. It's also offset from the planet's center by a third of the planet's radius. This creates an irregular, chaotic magnetosphere, radiation belts that wobble and shift, unpredictable exposure patterns. Navigating that environment without getting lethally irradiated would require precise knowledge of the magnetic field structure, knowledge we don't have, can't have without more missions. And those missions would be robotic precisely because sending humans through unknown radiation fields is insane. Let's say you somehow survived the journey, somehow endured 15 years of cosmic ray exposure, somehow made it through the radiation belts. You'd arrive at Uranus physiologically compromised, increased cancer risk, degraded cognitive function, damaged cardiovascular system, weakened immune response. And you'd still have to survive there for however long the mission requires. Then make the return journey, another 15 years of radiation exposure. The cumulative dose would be unprecedented. We've never exposed humans to radiation levels even close to what a Uranus mission would require. The longest deep space missions have been lunar landings, days, not years. Astronauts on those missions received measurable radiation doses, acceptable for short durations, completely unacceptable when multiplied by thousands. ISS astronauts, protected by Earth's magnetosphere, still face elevated cancer risk. 6 months on the station increases cancer probability measurably. They're in low Earth orbit, still partially shielded, still relatively close to Earth. And they're accumulating dangerous exposure. Deep space is worse, significantly worse. The radiation environment beyond Earth's magnetic field is fundamentally more hostile. And there's no escape, no safe room to retreat to. No way to reduce exposure except massive shielding you can't afford to carry. Some scientists propose using pharmaceuticals, radiation countermeasures, drugs that help cells repair damage or protect against radiation effects. They exist. They help. They're not nearly enough. You can't drug your way through 30 years of cosmic ray bombardment. The damage accumulates faster than any medication can repair it. Others suggest genetic modification. Engineer humans with enhanced DNA repair mechanisms. More efficient cellular cleanup systems. Maybe that works. Maybe we could create radiation-resistant humans. But that's not technology we have now. That's speculative biotechnology that might be possible someday. And even if it worked, you're talking about fundamentally altering human biology to make space travel survivable. That's not exploration. That's adaptation on a genetic level. The radiation problem has no current solution. It's not engineering, it's physics. High-energy particles exist. They penetrate matter. They damage biological tissue. You can reduce exposure with shielding. You can accept some level of damage, but you can't eliminate the problem without protection. We can't build with acceptable mass. Every added day of travel time increases cumulative radiation dose. Faster propulsion helps. Get there quicker, less exposure. Except faster propulsion requires more fuel, which increases mass, which requires more fuel. The rocket equation strikes again. You're trapped between radiation exposure and fuel requirements. Optimize one, the other gets worse. This is why robotic missions make sense for distant planets. Radiation doesn't affect electronics the same way it affects biology. You can harden circuits, shield sensitive components, accept some degradation. A robot exposed to lethal radiation doses can still function. A human exposed to those same doses dies. Voyager 2 survived the Uranus radiation belts, transmitted data, continued its mission. It's still operating today, 47 years after launch, because it's a machine. It doesn't have DNA to damage, no cells to destroy, no brain to deteriorate. Humans are fragile. Biological systems require specific conditions: stable temperature, breathable atmosphere, protection from radiation. We evolved for Earth. We're adapted to Earth's environment. Taking humans to Uranus means dragging Earth's environment with you. Life support, shielding, all the mass and complexity required to keep fragile biology functioning in a hostile environment. And for what? What can humans do at Uranus that robots can't? Collect samples. Robots can do that. Make observations? Instruments do that better. Conduct experiments. Automated systems are more reliable. The only advantage humans offer is adaptability, problem solving, creative thinking. But those advantages have to outweigh the massive costs and risks of keeping humans alive for 3 decades. They don't. The math doesn't work. The biology doesn't work. The radiation exposure alone makes human missions to Uranus irrational with current technology. You're not sending explorers, you're sending people to accumulate radiation damage for 30 years before dying of cancer shortly after return. If they return. That's not exploration. That's slow suicide. The universe is indifferent to human ambition. Physics doesn't care about our desire to explore. Radiation doesn't respect courage or determination. The distances are real. The exposure is real. The biological damage is real. And no amount of engineering can change the fundamental fact that humans are poorly suited for deep space travel. We're planetary creatures. We evolved in gravity, surrounded by atmosphere, protected by a magnetic field. Take away those protections, and we start breaking down, slowly but inevitably. Radiation is just one more way the universe reminds us we're not meant for the void. Human missions to Uranus aren't just difficult. They're not just dangerous. They're biologically destructive on a timescale we've never tested. We're talking about exposing humans to conditions that will definitely cause cancer, probably cause cognitive decline, and possibly cause organ failure. For 30 years, with no possibility of medical intervention beyond what you can carry. And even if you accept all that damage as the price of exploration, you still haven't solved propulsion, still haven't solved life support, still haven't addressed the psychological collapse that comes with decades of isolation. Radiation is just one more insurmountable barrier stacked on top of all the others. Human bodies aren't designed for this. Human psychology isn't designed for this. Our technology isn't capable of protecting us from this. Every aspect of a Uranus mission pushes human limitations beyond breaking points we haven't even approached in controlled environments. This is the reality of deep space. It's not noble. It's not heroic. It's just destructive. The radiation alone would ensure that anyone reaching Uranus arrived damaged, returned damaged, died damaged. That's if everything else somehow worked perfectly. It won't. Life support creates its own cascade of impossibilities. Every human needs approximately 5 kilograms of consumables daily. Oxygen, water, food. That's 1,825 kilograms per person per year. For a 30-year round trip, that's 54,750 kilograms per person. Just consumables. Before you account for the systems needed to store, process, and deliver those consumables, The International Space Station has regular resupply missions. Every few months, cargo spacecraft bring fresh supplies, water, food, equipment. That option doesn't exist for Uranus. There's no resupply, no refueling, no emergency extraction. Everything required for 3 decades must be carried from day one. Current life support systems aren't designed for complete self-sufficiency. The ISS recycles water, but it doesn't achieve 100% efficiency. There's loss, waste, systems degrade, filters need replacement. Even with recycling, you need reserves, backups, redundancy. For a Mars mission lasting 18 months, NASA's planning regenerative life support technologies, systems that recycle air and water with minimal loss. Even those systems require some resupply reserves. For foreseeable future technology, complete closure of the life support loop remains impossible. Uranus isn't 18 months. It's 360 months minimum. The math becomes absurd. You're not just carrying consumables for the crew. You're carrying spares for every life support component. Replacement filters, backup pumps, redundant scrubbers. Because if your CO2 removal system fails 15 years into the mission, everyone dies. No repair shipment is coming. Water recycling presents particular challenges. Human bodies produce approximately 3.89 kilograms of liquid waste daily. That waste must be purified back into drinking water. The ISS does this, but the ISS has backup systems, ground support, the ability to troubleshoot problems with engineers on Earth. At Uranus, radio signals take over 2.5 hours to reach Earth. Round-trip communication delay exceeds 5 hours. When something breaks, you can't ask for help and get immediate guidance. By the time Earth receives your distress call and responds, your crew might already be dead. This communication lag doesn't just affect emergencies. It shapes every aspect of the mission. Psychological support that works for ISS astronauts becomes useless. Real-time counseling sessions, impossible. Family video calls, a conversation with 5-hour delays between responses, isn't a conversation. It's exchanging messages with the past. The psychological research is clear. Astronauts on current missions experience significant mental health challenges. NASA data shows 22.8% of male astronauts and 85.2% of female astronauts exhibit anxiety symptoms. Depression affects 34.8% of male astronauts and 43.2% of female astronauts. Those numbers come from missions lasting months, with regular communication, with the knowledge that Earth is right there, visible in the sky. Uranus missions eliminate those comforts. Earth becomes an insignificant dot, then disappears entirely. The phenomenon has a name: Earth out of view. Researchers studying Mars missions identified it as a major psychological stressor. Mars is close compared to Uranus. Mars missions maintain some semblance of connection to home. Uranus missions offer complete isolation. Decades of it, in a confined metal tube, with the same few people, breathing recycled air, drinking recycled urine, eating the same shelf-stable meals for 30 years, watching equipment slowly degrade around you, knowing that any critical failure means death, and there's nothing you can do about it. Valentin Lebedev, a Soviet cosmonaut, documented his psychological decline during a 7-month space station mission. 7 months. He struggled with depression, interpersonal conflicts, cognitive difficulties. That was with Earth visible outside the window, with regular communication. with the certain knowledge that his mission had an end date. Scale that to 30 years. Remove all connection to Earth. Add the knowledge that you're accumulating irreversible radiation damage, that your cognitive function is declining, that you might not survive the return journey even if everything goes perfectly. The psychological collapse isn't a possibility, it's guaranteed. Researchers studying Mars missions acknowledge that stress levels for deep space missions will be significantly higher than anything tested in Earth orbit. They consider psychological breakdown a serious threat to mission success. Mars is a 3-year round trip in optimistic scenarios. Uranus is 10 times that duration. Human psychology wasn't designed for this. Our brains evolved for communities, social interaction, varied environments, natural cycles. Space missions eliminate all of that. Replace it with monotony, confinement, isolation, artificial everything. You can train for this: psychological screening, team compatibility assessments, practice isolation. But training for months doesn't prepare you for decades. The longest space mission in history was Valery Polyakov's 437 days aboard Mir. That's barely over a year. Even that pushed human endurance to its limits. Multiply that by 30, there's no precedent, no data, no way to know what happens to human psychology during 3 decades in a metal can. But the trajectory is clear. Extended isolation causes depression, anxiety, cognitive decline, interpersonal conflict. Those problems compound over time. They don't stabilize. They worsen. And unlike physical systems, you can't pack spare psychology, can't carry replacement mental health. Once a crew member breaks psychologically, there's no fix. Medication has limited effectiveness for situational depression caused by objective hopelessness. Therapy requires communication, which requires Earth, which is 5 light hours away. The mission planners know this. It's why every serious proposal for deep space missions emphasizes crew selection and psychological support. But those proposals target Mars. 3 years, maybe 5, not 30. 30 years exceeds human capacity for sustained isolation. Period. Some people last longer than others. Some handle confinement better. But everyone has limits. And 3 decades in a spacecraft will find those limits, then exceed them, then keep going. This isn't speculation. It's extrapolation from existing data on human psychology in extreme environments. Antarctic research stations, submarines, space stations. Every isolated environment shows the same patterns. Humans cope initially, then adaptation, then slow psychological erosion. The longer the isolation, the worse the decline. And space adds factors that Antarctic stations and submarines don't face. Radiation exposure, microgravity health effects, the absolute certainty that you cannot leave. A submarine can surface, an Antarctic station can be evacuated. A spacecraft to Uranus cannot turn around, cannot abort. Once you're committed for 3 decades. The life support requirements compound the psychological stress. You're not just isolated. You're dependent on machines for every breath, every drop of water, every calorie. Those machines will fail. Systems designed for years, not decades. Redundancy helps, but only delays the inevitable. When the water recycling system develops a leak 15 years in, and you're rationing water while trying to repair it with degraded spare parts, the psychological impact isn't abstract. It's immediate, visceral. You're watching your survival margin shrink, and there's no rescue coming. This is where human missions diverge completely from robotic missions. Voyager 2's cameras failed, its scan platform seized, systems degraded, but the spacecraft continued, transmitted data using remaining functional systems, adapted its mission profile to work around failures. Humans can't do that. When life support fails, humans die. There's no working around it. No mission adaptation, no graceful degradation. It's binary, functional systems, or death. And after 15 years in deep space, systems won't be functional. They'll be barely operational, held together by improvisation and prayer. Because you can't carry enough spares for 30 years of wear, can't predict every failure mode, can't manufacture replacement parts in a spacecraft machine shop. The ISS has the advantage of Earth's industrial base. When something breaks, engineers on the ground can design solutions, manufacture custom parts, send them up on the next resupply mission. That support infrastructure makes long-duration space habitation possible. Remove it, and the equation changes completely. You're on your own, with whatever you carried, for 3 decades. NASA understands this. Their technology development programs focus on increasing life support, reliability, and self-sufficiency. Closed-loop systems, bioregenerative life support, using plants and microorganisms to recycle waste. These technologies might work for Mars, might enable 5-year missions with minimal resupply. They're nowhere near capable of supporting 30-year missions. The biological systems required for true closed-loop life support don't exist. The engineering challenges of maintaining complex recycling systems for decades haven't been solved. And even if they were solved tomorrow, you still face the fundamental problem. Humans are the weak link. Plants can survive in controlled environments indefinitely. Microorganisms reproduce and replace themselves. Mechanical systems can be designed for extreme longevity. But humans? Humans break down. Physically from radiation, psychologically from isolation, socially from confined proximity to the same individuals for decades. There's no engineering solution to human fragility, no technology that makes humans suitable for 30-year deep space missions. We can improve life support, enhance radiation shielding, optimize psychological support, but we can't change fundamental human biology and psychology. You're still sending people into an environment that will destroy them. Slowly, inevitably. The life support might function perfectly. The radiation shielding might work exactly as designed. The mission timeline might proceed without a single technical failure. And the crew will still arrive at Uranus psychologically damaged, cognitively impaired, physiologically degraded. That's the baseline. That's the best-case scenario where everything goes right, where no critical systems fail, where interpersonal dynamics remain stable, where psychological resilience exceeds all historical precedent. Even then, you're looking at a crew barely capable of functioning after 15 years in transit, and they still have to do the mission. Whatever scientific objectives justified sending humans, whatever observations or samples or experiments require human presence, the damaged, exhausted crew has to perform those tasks, then survive another 15 years for the return journey. The return journey doesn't get easier, it gets harder. Systems are older, more degraded, supplies are depleted, psychological reserves are exhausted. The crew knows they're going home, but home is still 15 years away, and they're starting that journey already broken. This is why serious mission planners don't propose human missions to Uranus. Why the Decadal Survey recommends robotic missions. Why every credible analysis concludes that human presence at Uranus offers no advantages worth the costs and risks. The life support challenges alone make human missions irrational. Before considering propulsion, before addressing radiation, before calculating fuel requirements, just keeping humans alive for 30 years in a closed system exceeds our current capabilities and our foreseeable capabilities, and possibly our theoretical capabilities given fundamental constraints on closed-loop biological systems. You can't pack 30 years of consumables, can't guarantee 30 years of system reliability, can't maintain human psychology through 3 decades of isolation. Each problem is insurmountable individually. Together, they create a wall of impossibility that no amount of engineering can breach. The universe doesn't care about human determination. Physics doesn't respect courage. Biology doesn't accommodate ambition. The requirements for keeping humans alive at Uranus exceed what human technology can provide. Not might exceed, do exceed. Definitively, absolutely. This isn't a challenge to overcome. It's a boundary condition of reality. Humans can't survive 30-year missions with current technology, can't maintain psychological health through decades of isolation, can't guarantee life support system reliability over such timescales. These aren't engineering problems with engineering solutions. They're fundamental limitations of human biology encountering the reality of deep space. Human missions to Uranus remain impossible because humans themselves are the limiting factor. We're adapted for Earth, dependent on Earth's environment. Remove that environment and we start dying, slowly with radiation, psychologically with isolation, mechanically as life support systems degrade beyond repair. Send robots. They don't need psychology. Don't accumulate radiation damage that matters. Don't require decades of consumables. Don't break down from isolation. They're designed for the mission. Humans aren't. Human Uranus missions fail before they start because the mission requirements exceed human capabilities by orders of magnitude. Not slightly, not marginally, completely. Human biology sets the limits, and those limits fall far short of Uranus. The fundamental barrier isn't technological, it's mathematical. Tsiolkovsky's rocket equation governs every aspect of spaceflight, and it's merciless. The equation tells you how much fuel you need to achieve a given change in velocity. Sounds simple, except the fuel itself has mass, which means you need more fuel to accelerate the fuel, which adds more mass, requiring more fuel, which adds more mass. It's exponential, vicious, unforgiving. For a trip to Mars, this equation is manageable, barely. For Uranus, it becomes absurd. Consider what a crewed mission requires. You need fuel to escape Earth's gravity, fuel to accelerate toward Uranus, more fuel to decelerate when you arrive, even more fuel to enter orbit, then fuel to leave orbit, fuel to accelerate back toward Earth, and fuel to decelerate for Earth re-entry. Each phase requires enormous delta V, velocity change, and each delta V requirement multiplies your fuel needs exponentially. Run the numbers for a conventional chemical rocket. You'd need a fuel tank larger than a skyscraper to move a capsule the size of a minivan. That's not hyperbole. That's the rocket equation. Chemical propulsion maxes out around 450 seconds of specific impulse. That's the efficiency metric. How much thrust you get per unit of fuel. For Uranus, you need better. Much better. Nuclear thermal propulsion offers roughly 900 seconds, double the efficiency. Sounds promising until you calculate the fuel mass for a 30-year round trip. Still absurd, still impossible. Plasma propulsion reaches 8,000 seconds of specific impulse. Now we're talking. Except plasma thrusters produce almost no thrust. They're efficient but weak, great for satellite station keeping, useless for moving crew-sized payloads across the solar system in reasonable timeframes. You could run a plasma thruster for years, decades even, slowly building velocity. But that extended burn time requires carrying fuel for the entire duration. Which brings you back to the mass problem. The rocket equation always wins. Here's where it gets worse. Everything discussed so far assumes you're just moving the spacecraft, just the structure and fuel. Now add humans, life support systems, radiation shielding, food, water, backup systems, medical equipment, scientific instruments, the habitat module, the return vehicle. Every kilogram of payload multiplies the fuel requirement exponentially. A crewed spacecraft to Uranus would mass hundreds of tons, possibly thousands, just the spacecraft, before fuel. The fuel mass to move that payload becomes incomprehensible. Millions of tons, tens of millions. No launch system exists that can put that much mass into orbit. Not even close. You'd need hundreds of launches, thousands maybe, assembling the spacecraft in orbit, ferrying up fuel in segments. Each launch costs tens of millions of dollars, minimum. You're looking at launch costs alone exceeding the GDP of small nations. And that's before addressing the fundamental problem. Even if you could assemble this massive spacecraft in orbit, even if you could somehow afford it, the fuel requirements for the return journey make it impossible. Because here's what nobody talks about. The fuel for the return journey has to travel to Uranus with you. Read that again. The fuel for coming home travels outbound, the entire way. That fuel has mass, enormous mass, which means you need even more fuel to accelerate that return fuel to Uranus, which adds more mass, requiring more fuel. The rocket equation compounds, multiplies, explodes. Some proposals suggest refueling at Uranus, manufacturing fuel from local resources. Except Uranus has no solid surface, just atmosphere transitioning to liquid layers, transitioning to exotic ice phases under crushing pressure. Where exactly are you mining resources? How are you processing them? What infrastructure converts Uranian atmosphere into rocket fuel? These questions have no answers, because the concept is fantasy. Other proposals suggest one-way missions. Send the crew, let them die at Uranus. That's not exploration, that's execution. No space agency will approve suicide missions. No crew would volunteer for guaranteed death. No ethical framework permits deliberately stranding humans at Uranus. The fuel problem alone makes crewed missions impossible. Before considering any other challenge, but let's consider them anyway. Slowing down at Uranus requires massive fuel expenditure. You're traveling at tens of kilometers per second. Relative to Uranus, to enter orbit, you need to shed that velocity, which means burning fuel, lots of fuel, all of which you carried from Earth. The alternative is aerobraking, using atmospheric friction to slow down. Mars missions could theoretically aerobrake. Mars has atmosphere, thin but present. Uranus has atmosphere too, except you can't aerobrake there. The atmosphere extends thousands of kilometers deep, with no solid surface. You'd enter the atmosphere, start slowing, keep slowing, descending deeper, where pressure increases, temperature rises, and you just keep falling. into regions where the atmospheric pressure exceeds anything your spacecraft could withstand. There's no shallow atmospheric layer for gentle braking. It's all or nothing, and all means destruction. So you can't aerobrake, must use fuel, which you don't have enough of. Even if you somehow solve the outbound fuel problem, the return journey faces identical challenges. You need to escape Uranus's gravity. That requires fuel. Lots of fuel, which you'd need to land on Uranus with, except you can't land on Uranus, because there's no surface, so you'd orbit. Conducting your mission from orbit, then fire engines to escape orbit, accelerate toward Earth. That escape burn requires enormous delta V. Uranus is massive. Its gravity well is deep. The fuel for that single burn would mass more than the entire Apollo program's spacecraft, multiple times over. Then you need fuel to decelerate at Earth, to slow down enough for atmospheric re-entry. Coming in too fast means burning up. Too slow means you don't have enough velocity to return in reasonable time. The fuel budget for Earth approach and capture is substantial, all of which traveled to Uranus and back. Add it up, every phase, every burn, every velocity change. The total fuel requirement exceeds what's physically possible to launch from Earth by orders of magnitude. Not difficult, impossible. Some futurists propose in-space refueling, fuel depots at various points, staging areas. Where's the fuel coming from? Who's maintaining these depots? How do you keep cryogenic propellants from boiling off over decades? These aren't details to work out later. They're fundamental impossibilities masquerading as engineering challenges. The laws of orbital mechanics don't care about optimism. The rocket equation doesn't bend for determination. Physics sets the boundaries, and those boundaries exclude crewed Uranus missions. You could potentially reduce fuel requirements with different propulsion systems. Nuclear pulse propulsion, detonating nuclear bombs behind the spacecraft for thrust. Sounds insane, because it is. The engineering challenges are staggering, the political obstacles insurmountable, the radiation exposure catastrophic. And even if you built it, even if you launched it, you're still bound by fundamental energy requirements. Moving mass across the solar system requires energy. That energy comes from somewhere. Chemical bonds, nuclear reactions. Whatever the source, you're carrying it with you, which adds mass, requiring more energy, adding more mass. There's no escape from this logic. No clever engineering that bypasses physics. The fuel problem represents a hard wall, an absolute barrier. Human missions to Uranus fail on propulsion alone, before life support, before radiation, before psychology. The rocket equation kills the mission in the planning stage. Some advocates point to future technology, fusion drives, antimatter propulsion, breakthrough physics. Sure, invent those, then we'll talk. Until then, we're working with known physics, real engineering, actual constraints, and those constraints make crewed Uranus missions impossible, not improbable, not challenging, impossible. The math doesn't work, the physics doesn't permit it, the engineering cannot solve it. This isn't pessimism, it's arithmetic. Every credible mission analysis reaches identical conclusions. The fuel requirements exceed available resources by factors of hundreds, thousands. You can't engineer around that gap, can't innovate past it, can't determine your way through it. The universe doesn't negotiate. Physics doesn't compromise. The propulsion challenge stands alone as sufficient reason to abandon crewed Uranus missions. Everything else is additional impossibility layered on top. But the fuel problem is foundational, unsurmountable, absolute. Robotic missions face the same rocket equation, but robots don't need life support, don't require return fuel, can operate on minimal power. Voyager 2 reached Uranus on a gravity assist trajectory, no fuel for slowing down, just a flyby. That's what's possible. High-speed reconnaissance, not crude exploration. Future robotic missions might orbit, conduct detailed studies, deploy probes, all achievable with chemical propulsion and gravity assists. No exotic technology required, because robots don't come home, don't need fuel for return, don't require the exponential mass multiplication that kills crewed missions. The fuel problem doesn't just make crewed missions difficult, it makes them thermodynamically irrational. You'd spend more energy sending humans to Uranus than those humans could possibly justify through scientific return. The energy budget alone argues for robots, before considering safety, before addressing ethics. From pure efficiency standpoint, crewed missions waste resources on a scale that borders on criminal, especially when robots can accomplish the same objectives, better in many cases, without risking lives, without impossible fuel requirements, without violating physics. The propulsion barrier isn't something we might overcome eventually. It's fundamental, built into how the universe works. Unless physics changes, unless the rocket equation somehow becomes less tyrannical, crewed Uranus missions remain fantasy. Dangerous fantasy that diverts resources from achievable goals. We should explore Uranus. Absolutely. Send sophisticated robots, advanced AI systems, cutting-edge instruments. Learn everything possible about this strange ice giant. But sending humans serves no purpose, solves no problem, achieves no objective that justifies the cost and impossibility. The fuel requirements alone provide sufficient reason to never attempt it. Everything else is just additional confirmation of the same conclusion. Crewed Uranus missions fail on physics, math, thermodynamics, before the first rivet is placed, before the first test, before anything physical exists. The numbers say no, definitively, absolutely. And unlike human opinion, numbers don't change based on enthusiasm or political pressure. The rocket equation remains unyielding, merciless, rendering crewed Uranus missions impossible regardless of technological advancement or budgetary commitment. This is the wall you hit before addressing any other challenge. The wall built from mathematics and physics. The wall that doesn't move. Human crews can't reach Uranus because they can't carry enough fuel, can't solve the rocket equation, can't overcome the exponential mass growth that dooms the mission before it starts. The fuel problem stands as permanent barrier, unsurmountable by any known or foreseeable technology. This isn't the only reason crewed Uranus missions fail, but it's sufficient reason all by itself. Human missions to Uranus die in the propulsion calculations, where physics meets ambition and physics wins, every single time. Suppose you solve the fuel problem somehow. Imagine infinite energy or magical propulsion that breaks physics. The mission still fails, because the environment at Uranus kills you anyway. Minus 371 degrees Fahrenheit. That's the temperature in Uranus's tropopause, the coldest planetary atmosphere in the solar system. Not Mars, not Neptune, Uranus. This ice giant holds the record for atmospheric cold that makes Antarctic winter look tropical. Average temperature across the planet hovers around -350 Fahrenheit, not briefly, not in specific locations, everywhere, constantly. The entire atmosphere maintains temperatures that freeze methane solid, that liquefy hydrogen, that make titanium brittle as glass. No thermal protection system exists for these conditions, not for long-term exposure, not for human survival. ISS thermal systems handle 250-degree temperature swings between sunlight and shadow. Mars rovers survive -130 Fahrenheit nights. Uranus laughs at these numbers. The engineering challenge scales exponentially. Every material changes properties at these temperatures. Metals contract, plastics shatter, lubricants freeze solid, electronics fail, batteries die, chemical reactions stop. The spacecraft becomes a frozen tomb before you arrive. But temperature represents just the beginning. Wind speeds at Uranus reach 560 miles per hour. Hurricane-force winds that make Earth's strongest storms look calm. These aren't occasional gusts. They're constant atmospheric features. Jet streams of hydrogen and helium screaming through the upper atmosphere at speeds that tear structures apart. You can't land on Uranus anyway. No solid surface exists. The atmosphere gradually transitions into liquid layers, then ice, then rock core. There's no surface to set down on, just increasing pressure and density until your spacecraft gets crushed. Scientists define Uranus's surface as the point where atmospheric pressure equals 1 bar. Arbitrary definition, convenient for calculations, meaningless for actual landing. At that pressure level, you're still surrounded by hydrogen and helium atmosphere, still exposed to crushing winds, still experiencing temperatures that freeze everything solid. Descending deeper makes conditions worse. Pressure increases. Temperature rises eventually, but remains incompatible with human survival. The transition from atmosphere to liquid isn't distinct. You don't hit water like landing in an ocean. You gradually compress into denser and denser fluid until the spacecraft implodes. The atmospheric composition kills you faster than temperature or pressure. 83% hydrogen, 15% helium, 2% methane, 0 oxygen, trace amounts of other compounds, all toxic. You can't breathe it, can't process it, can't survive in it for seconds without life support. Methane creates the planet's blue-green color, absorbs red wavelengths from sunlight, reflects blue and green back into space. Beautiful from a distance, deadly up close. Methane at these pressures and temperatures behaves nothing like the gas we use on Earth. It forms ice crystals, creates clouds, participates in chemistry that we barely understand. Sunlight intensity at Uranus drops to 1/400th Earth's level. The planet orbits 19 times farther from the Sun than Earth does. Light follows the inverse square law. Distance increases by 19, intensity drops by 361. Solar panels become nearly useless. Nuclear power becomes mandatory, but nuclear reactors add mass, complexity, failure points. The extreme axial tilt creates seasons unlike anything in human experience. Uranus rotates on its side, 97.77-degree tilt. One pole faces the Sun for 42 Earth years. Then the other pole gets 42 years of sunlight. Each hemisphere experiences decades of continuous darkness, followed by decades of continuous light. During the dark decades, temperatures drop even further. The already frozen atmosphere gets colder. Wind patterns shift. The planet's energy balance changes. Arriving during the wrong season means even worse conditions. if such distinctions matter when all conditions are lethal. Uranus radiates almost no internal heat. Neptune, similar size and composition, radiates 2.61 times more energy than it receives from the Sun. Jupiter radiates twice what it receives. Saturn radiates 1.8 times. Uranus? Barely any excess heat at all. It's the only planet that doesn't give off more heat than it receives. Why? Nobody knows for certain. Theories range from that ancient collision that tilted the planet to unusual internal structure. The mystery remains unsolved, but the consequence is clear. Uranus is cold, profoundly cold, unnaturally cold for a gas giant. And that cold makes survival impossible. The magnetic field presents additional nightmares. Most planets have magnetic fields aligned roughly with their rotation axis. Earth's magnetic poles sit near the geographic poles. Mars had a magnetic field once. Jupiter's is powerful and regular. Uranus, tilted 60 degrees from the rotation axis, offset from the planet's center by 1/3 of its radius. This creates a lopsided, irregular magnetosphere, unlike anything else in the solar system. The magnetic field wobbles as the planet rotates, changes orientation, exposes different regions to radiation at different times, creates unpredictable radiation environments that make shielding nearly impossible. Voyager 2 discovered intense electron radiation belts at Uranus, second only to Jupiter's in intensity. How these belts form and persist without an obvious plasma source remains mysterious, but they exist. Bombarding anything in Uranus' orbit with high-energy particles that destroy electronics and damage biological tissue. Recent research suggests Voyager 2 might have observed Uranus during unusual conditions. The magnetosphere appeared compressed, plasma depleted, possibly representing conditions that exist less than 5% of the time. If Voyager had arrived days earlier, the solar wind pressure would have been 20 times lower. The magnetosphere dramatically different. This uncertainty makes mission planning impossible. You can't design radiation shielding when you don't know what radiation environment you'll encounter. Can't predict safe orbits. Can't calculate exposure limits. The data from Voyager 2 might represent an anomaly or typical conditions. Nobody knows. Communication delays compound every other problem. Light takes 2 hours 40 minutes to travel from the Sun to Uranus. Radio signals, traveling at light speed, face the same delay. Round-trip communication with Earth takes over 5 hours minimum, often longer depending on orbital positions. This delay eliminates real-time mission control. No immediate guidance during emergencies. No quick consultations with engineers. No instant access to Earth's resources and expertise. The crew operates autonomously or dies waiting for responses that arrive hours after they're needed. Compared to ISS missions, communication delay measured in milliseconds. Ground control provides constant support. Problems get solved collaboratively in real time. Expertise from thousands of engineers available instantly. None of this exists at Uranus. Mars missions face communication delays up to 44 minutes round trip. Challenging but manageable. Crews can operate semi-autonomously. Wait for responses during non-critical periods. Develop procedures accounting for delay. Uranus delays are 7 times longer. Crossing the threshold from difficult to impossible. Medical emergencies become death sentences. Appendicitis that's treatable on ISS becomes fatal at Uranus. Equipment failures that ground control helps diagnose become mission-ending catastrophes. Psychological crises that benefit from real-time counseling spiral into disasters. The communication delay transforms manageable problems into fatal ones. The isolation weighs heavier than physical distance suggests. On ISS, Earth fills your window. Blue marble hanging in black space. Familiar continents, recognizable weather patterns, visual connection to home. Mars crews will see Earth as a bright star, distant but visible, still part of the sky. From Uranus, Earth becomes invisible, lost in the sun's glare, indistinguishable from background stars. The psychological impact of Earth out of view phenomenon affects Mars crews profoundly. Uranus crews would experience it multiplied beyond measure, floating in darkness at the edge of the solar system. Home not just distant but invisible, gone from sight, removed from consciousness. Every mission parameter works against human survival. Temperature kills you, pressure crushes you, atmosphere poisons you, radiation destroys you, distance isolates you, communication delay abandons you, darkness surrounds you, wind tears at you. The environment stacks impossibilities until the mission collapses under accumulated weight. You can't engineer around all these problems simultaneously. Solving one creates contradictions with others. Heavy radiation shielding increases mass, requiring more fuel, violating the rocket equation. Better life support systems add complexity, increasing failure probability. Robust thermal protection adds bulk, making spacecraft less maneuverable in extreme winds. The engineering trade-offs become circular. Every solution creates new problems. Every fix generates new requirements. The design space collapses. No configuration satisfies all constraints. The mission becomes mathematically impossible before addressing human factors. Uranus's environment didn't evolve to be hostile. It's indifferent. The planet doesn't care about human survival. Operates according to physics and chemistry that predate human existence by billions of years. The conditions aren't punishment, they're simply reality. But reality that's incompatible with human biology. We evolved for Earth. Specific temperature range, particular atmospheric pressure, defined chemical composition, certain radiation environment, gravitational pull we're built for. Removing any single parameter kills us. Uranus removes all of them, simultaneously, permanently. The planet represents the antithesis of human survivable conditions. If you designed an environment specifically to kill humans efficiently, you'd struggle to improve on Uranus. Everything about it contradicts everything we need to live. Some argue technology will advance. Better materials, improved thermal systems, enhanced radiation shielding. These arguments ignore scale. The gulf between Earth conditions and Uranus conditions is too vast. Technology can't bridge it. Not because we lack cleverness, because physics sets limits. Thermal protection that maintains shirt sleeve temperature inside, while outside reads -371 requires energy. Enormous amounts. Continuous supply. For years. Decades potentially. Where does this energy come from? How do you generate it? How do you radiate waste heat in an atmosphere that's already colder than anything thermal systems are designed for? Radiation shielding that blocks Uranus's electron belts requires mass. Substantial mass. Water works well. Lead works better, but both add tons to spacecraft already struggling with the rocket equation. The shielding mass alone might exceed practical limits before addressing any other system. Life support providing breathable atmosphere in hydrogen-helium environment requires perfect sealing. Zero leaks. For years. in temperature extremes that make materials brittle, in pressure differentials that stress every joint, with vibration from constant winds, while radiation degrades polymers and metals. The engineering challenge approaches impossibility. The environment at Uranus doesn't just make the mission difficult, it makes survival impossible. Not theoretically impossible, practically impossible. The conditions exceed human tolerance by margins too large to engineer around. You can't design for these extremes, can't test for them, can't simulate them accurately, can't validate systems under conditions that don't exist anywhere accessible. The engineering becomes guesswork, building for environments you can't replicate, hoping materials behave as predicted, trusting models over experience. This approach works for robotic missions. Voyager 2 survived Uranus flyby, operated in the environment briefly, collected data, continued to Neptune. Success. But robots tolerate conditions humans can't. Don't need life support, don't require thermal comfort, don't suffer psychological effects, can be designed for one-way missions without ethical problems. Humans need everything working perfectly, continuously, for years. One failure cascade kills everyone. The environment provides no margin for error, no safe havens, no rescue possibility, no backup plans that mean anything across billions of miles and years of travel time. The temperature, pressure, composition, radiation, isolation, and communication delays combine into a matrix of impossibility. Each factor alone presents serious challenges. Together, they create an environment fundamentally incompatible with human presence. This isn't pessimism, it's physics. The numbers don't care about human ambition. The environment doesn't adjust for our limitations. Uranus exists as it is, indifferent to whether we can survive there. The answer is no, definitively. The environment itself provides conclusive evidence that human missions fail before they start. The return journey makes survival fantasy. Consider what bringing humans back requires. First, spacecraft must carry enough fuel to decelerate into Uranus orbit. Full stop from interplanetary velocity, enormous energy expenditure. Then remain operational during mission duration. Maintain all systems in hostile environment, then accelerate back toward Earth. Another massive energy requirement. The fuel needed for return exceeds the fuel needed for arrival. Significantly, because you're carrying return fuel the entire outbound journey, adding mass, requiring more fuel to move that fuel. The rocket equation compounds ruthlessly. Calculate the numbers. Minimum transit time to Uranus using gravity assist runs 13 years. Return journey faces similar duration. 26 years total, minimum. That assumes optimal planetary alignment both directions. Assumes no extended stay at Uranus. Assumes everything works perfectly. None of these assumptions hold under scrutiny. Life support for 26 years exceeds current capability. International Space Station requires regular resupply from Earth. Every few months, launches bringing food, water, spare parts, equipment. Without these shipments, ISS becomes uninhabitable rapidly. Now extend that timeline to decades, while traveling billions of miles from any resupply possibility. Each crew member needs 5 kilograms of consumables daily. Water dominates this mass, 3.54 kilograms per person per day. Oxygen adds 0.84 kilograms. Food contributes 0.62 kilograms. Multiply by crew size, multiply by 26 years. The mass becomes astronomical. Even with perfect recycling, Losses accumulate, systems degrade, efficiency drops, reserve supplies become mandatory. Water recycling on ISS recovers roughly 93%. Seems impressive until you calculate losses over years. 7% daily loss per person equals significant mass over time. That missing water must come from reserves, which must be carried from Earth. Adding launch mass, requiring more fuel. The equation spirals. Psychological factors worsen everything. NASA data shows 22.8% of male astronauts and 85.2% of female astronauts exhibit anxiety symptoms during missions. Depression affects 34.8% of males and 43.2% of females. These numbers come from relatively short duration missions, with Earth always visible, with communication delays measured in seconds, with knowledge that return happens soon. Uranus missions eliminate every psychological support. Earth becomes invisible, indistinguishable from background stars. The Earth out of view phenomenon creates profound isolation. Communication delays exceed 5 hours round trip. No real-time conversation, no immediate support, no connection to home beyond delayed text messages. Research on Mars mission psychology predicts 1 in 5 astronauts will develop anxiety-like behavior during deep space transit. 1 in 2.8 will experience memory impairments. Mars missions last 18 months. Uranus requires 26 years minimum. The psychological damage becomes catastrophic, irreversible, likely. Radiation exposure during return journey adds to outbound damage. Remember that every cell nucleus gets hit by hydrogen ions daily. HZE nuclei strike every few months. This continues throughout return transit. Years of additional exposure, compounding cellular damage, increasing cancer probability, degrading cognitive function further. By the time spacecraft reaches Earth orbit, crew members might lack the mental capacity to operate systems, if they're still alive. Equipment degradation over decades presents another insurmountable barrier. Spacecraft components aren't designed for 30-year operational lives, especially under Uranus environment stress. Cold makes materials brittle. Radiation breaks down polymers. Constant thermal cycling between sun exposure and shadow creates mechanical stress. Micrometeorite impacts accumulate. Systems fail. Redundancy helps initially. Backup systems compensate for primary failures, but redundancy adds mass, and eventually backups fail too. 26 years provides ample time for cascade failures. Critical systems breaking faster than repairs can address them. No spare parts available except what launched from Earth. Decades prior. Computer systems become obsolete during flight. Hardware designed in 2030 will be ancient by 2056. Software potentially incompatible with mission requirements that evolved. Communication protocols might change. Navigation systems could require updates impossible to implement. The technology gap creates operational nightmares. Medical emergencies doom return missions. Any serious injury or illness becomes fatal. No hospitals, no specialists, no equipment beyond what fits in spacecraft medical bay. Appendicitis kills, cancer kills, heart attack kills, stroke kills, infections kill. Dental problems become agonizing emergencies. Crew medical officer can't perform surgery beyond basic procedures, can't diagnose conditions requiring imaging equipment too massive to carry, can't treat complications from radiation exposure accumulating throughout mission. The isolation ensures no rescue. If spacecraft systems fail during return, everyone dies. No other vessels exist capable of intercept. No way to transfer crew to functional spacecraft. No abort options. Once return journey begins, crew commits to completing it or dying in attempt. Fuel requirements for return make mission mass impossible. Even with nuclear thermal propulsion offering twice the efficiency of chemical rockets, the fuel needed for deceleration, orbital operations, and return acceleration exceeds practical limits. Advanced plasma propulsion systems provide better efficiency. Specific impulse reaching 8,000 seconds. But these systems remain unproven for human missions. Lifetime limits prevent completing deep space journeys. The rocket equation destroys return mission feasibility. Every kilogram of return fuel must be accelerated from Earth, through interplanetary space, decelerated at Uranus, then accelerated again toward Earth. The fuel needed to move return fuel exceeds the return fuel itself, compounding exponentially, until spacecraft mass becomes impossible to launch. Orbital mechanics constrain departure windows severely. Can't leave Uranus whenever convenient. Must wait for planetary alignment. Optimal transfer orbits occur infrequently. Missing a window adds years to mission, years consuming life support, years accumulating radiation damage, years of psychological deterioration. Even assuming crew survives to departure window, achieving escape velocity from Uranus system requires substantial fuel. The planet's gravity, while weaker than Jupiter's, still demands significant energy to escape. Moons complicate trajectory planning. Radiation belts must be traversed during departure, adding exposure during vulnerable acceleration phase. The return trajectory lacks the gravity assist benefits available outbound. Jupiter might not be positioned advantageously. Using gravity assists extends mission duration. Direct return requires more fuel. Either option presents problems. Extended mission exceeds life support capacity. Direct return exceeds fuel capacity. No good choices exist. Communication during return journey provides no comfort. As distance from Earth decreases, delay decreases. But this happens gradually. For years, crew remains effectively isolated. By the time communication becomes reasonable, they're already deeply damaged psychologically. Radiation effects are irreversible. Physical deterioration is advanced. Deceleration into Earth orbit requires precision impossible after years in space. Navigation systems must function perfectly. Engines must fire exactly as calculated. Any error sends spacecraft past Earth, into solar orbit. Unrecoverable. Crew dies watching Earth recede. Even successful Earth orbit insertion doesn't guarantee survival. Re-entry from interplanetary velocity stresses spacecraft beyond typical tolerances. Heat shields designed for LEO return aren't adequate. Specialized re-entry systems add mass, which requires more fuel, which adds more mass. The equation remains unforgiving. Crew physical condition after 26 years in microgravity makes landing survival questionable. Bone density loss, muscle atrophy, cardiovascular deconditioning, vision problems, immune system degradation, radiation damage. These effects accumulate despite exercise and countermeasures. Bodies adapted to zero gravity can't handle re-entry acceleration. Multiple G-forces during descent could prove fatal. The economic absurdity of return missions deserves mention. Cost of sending humans to Uranus and returning them exceeds any conceivable benefit. Scientific data collection happens better with robots. Cheaper, safer, more reliable. No life support needed. No return fuel required. Robots don't develop anxiety or memory impairment, don't require medical care, don't consume resources, don't die. Voyager 2 reached Uranus, collected invaluable data, continued to Neptune, still operating after decades, cost fraction of human mission, provided better science than human crew could. This pattern holds throughout space exploration. Robots outperform humans for distant targets. The desire for human presence at Uranus reflects emotion rather than logic. Adventure, exploration, human achievement, noble sentiments. But sentiments don't overcome physics, don't solve engineering problems, don't resurrect dead crew members. Some argue technology will advance, better propulsion, improved shielding, enhanced life support. These arguments ignore timescales. Revolutionary propulsion systems require decades of development, testing, validation. Even optimistic projections push human Uranus missions beyond this century. By then, other technologies might make the trip obsolete, or reveal even more reasons it's impossible. The fantasy of Uranus colonies persists in popular imagination. Humans establishing permanent presence, mining resources, building infrastructure. This fantasy ignores every reality discussed. The environment kills, the distance isolates, the resources don't exist. Nothing about Uranus supports human habitation, not temporarily, certainly not permanently. Every parameter examined leads to the same conclusion. Human missions to Uranus can't return successfully. The outbound journey alone exceeds survival capability. Adding return requirements makes impossibility absolute. The fuel doesn't exist. The life support can't function that long. The radiation damage becomes lethal. The psychological toll destroys crew capability. The equipment fails. The isolation ensures no rescue. The economics make no sense. This isn't defeatism. It's acceptance of physical reality. Uranus exists as magnificent scientific target. For robots, for telescopes, for remote observation, not for human visitation. The planet represents boundary of human reach. Beyond this point, we observe rather than visit. Study rather than explore personally. Accept limitations rather than pretend they don't exist. The universe contains environments humans can't survive. Uranus exemplifies this category perfectly. Recognizing these limits doesn't diminish human achievement. It focuses effort on achievable goals. Mars might be reachable. Moon certainly is. Asteroids potentially. But ice giants remain forever beyond human touch. Future generations might develop technologies we can't imagine. Physics we don't understand. Capabilities that seem magical now. Perhaps they'll prove this analysis wrong. Develop solutions to problems that appear insurmountable today. But betting human lives on hypothetical future technology represents irresponsibility. Current physics and engineering provide clear verdict. Nobody who travels to Uranus is coming back. Not because of failure or accident. Because the trip itself makes return impossible. The distance, the environment, the duration, the isolation, the radiation, the fuel requirements, the life support limitations, the psychological damage, every factor combines into absolute barrier. The ice giant remains beautiful from distance, mysterious, fascinating, worthy of study, but human hands will never touch Uranus. Human eyes will never see it directly. Human feet will never stand on anything resembling its surface. The planet exists as eternal monument to the limits of human exploration, a boundary written in physics rather than choice. Some boundaries exist to be crossed, others exist to teach humility. Uranus teaches humility. The universe is vast. Most of it remains forever beyond our reach. We're limited beings in unlimited cosmos. Understanding these limits matters as much as testing them. Perhaps more. Human exploration continues elsewhere, closer to home, within the realm of possible rather than impossible, where return journeys work, where survival is challenging but achievable, where technology serves rather than fails. Uranus isn't that place. Will never be that place. The sooner we accept this reality, the sooner we focus effort productively. The planet spins on its side in the outer darkness, indifferent to human ambition, existing according to physical law. Those laws don't negotiate, don't compromise, don't care about human desires. They simply are. And they say clearly, definitively, permanently, you can't go to Uranus and come back. The return journey fails before it starts. Human ingenuity has limits. Physics imposes them. Uranus exemplifies where those limits become absolute. The ice giant remains out there, distant, cold, lethal, forever beyond the boundary of human survival. The first humans to reach Uranus aren't coming back, not because of some catastrophic failure we haven't anticipated, not because rescue becomes impossible, but because every single aspect of the journey violates the fundamental requirements for human survival and return. The fuel doesn't exist. The rocket equation remains merciless. Every kilogram of return propellant must be accelerated billions of miles, decelerated at Uranus, accelerated again toward Earth. The exponential mass growth makes the mission impossible before addressing any other constraint. Chemical propulsion fails. Nuclear thermal propulsion fails. Even theoretical plasma drives fail to solve the fundamental mathematics of moving humans across the solar system and back. The radiation accumulates relentlessly. Galactic cosmic rays tear through cells daily for decades. Uranus's intense electron belts rival Jupiter's ferocity. Shielding massive enough to provide protection exceeds what any rocket can launch. The cognitive damage starts immediately. Memory impairment, anxiety disorders, cellular destruction. By the time spacecraft reaches Uranus, crew members are already irreversibly damaged. The return journey compounds this damage beyond survival. Life support systems can't function for 30 years. Current technology requires resupply every few months. Water recycling loses 7% daily. Air systems degrade. Equipment fails. No closed-loop system exists capable of sustaining humans for decades without resupply. The engineering challenge isn't difficult. It's impossible with foreseeable technology. The psychological collapse is guaranteed. 26 years minimum in a metal tube. Same handful of people. Earth invisible among background stars. Communication delays exceeding 5 hours. No escape, no rescue, no relief. Research on much shorter missions already shows devastating mental health effects. Multiply those effects by factors of 10 or 20. The human mind wasn't built for this isolation. The environment itself kills you. Minus 371 degrees Fahrenheit. Winds exceeding 560 miles per hour. Atmosphere of hydrogen and helium. Radiation belts of inexplicable intensity. No solid surface to land on. No resources to extract. No way to survive outside spacecraft for even seconds. Uranus represents the antithesis of every condition humans require. The return journey requires fuel you can't carry, propulsion you don't have, life support that can't last, psychological resilience that doesn't exist, equipment reliability impossible to achieve. medical capabilities inadequate for inevitable emergencies. Every parameter works against survival. This isn't speculation about what might go wrong. It's acknowledgement of what must go wrong. The mission violates physics, exceeds biology, contradicts engineering, ignores mathematics. No amount of determination overcomes these realities. Some will argue that future technology might solve these problems. Revolutionary propulsion, perfect life support, enhanced human biology. These arguments confuse science fiction with engineering. Physics sets boundaries that cleverness can't circumvent. The rocket equation doesn't negotiate. Radiation damage doesn't reverse. Human psychology doesn't adapt to decades of isolation. The laws governing these phenomena are fundamental, not suggestions, not challenges to overcome, limits built into how the universe operates. Robotic missions work beautifully. Voyager 2 proved this, operating for decades, surviving conditions that would kill humans instantly, collecting data impossible to gather otherwise. Future robotic missions will explore Uranus in detail, map its atmosphere, study its moons, analyze its magnetic field, provide scientific understanding beyond what human crews could achieve, without risking lives, without impossible fuel requirements, without violating physics. The persistent fantasy of human missions to distant planets reflects emotion rather than reason. The desire to plant flags, to stand on alien worlds, to push human boundaries ever outward. Noble impulses, but impulses that don't override physical reality. Uranus exists beyond the boundary of human reach, not temporarily, permanently, unless physics changes, unless biology transforms, unless engineering discovers principles we can't currently imagine. Accepting this limitation doesn't diminish human achievement. It focuses effort productively. Mars might be reachable, asteroids potentially, moons of Jupiter perhaps with revolutionary technology, but ice giants remain forever beyond human touch. This represents wisdom rather than defeat. Understanding where boundaries exist prevents wasting resources on impossible goals. The universe contains wonders humans will never experience directly. Neutron stars will never visit. Black holes will never approach. Distant galaxies will never reach. Uranus joins this category, observable from distance, studyable through instruments, understandable through science, but untouchable by human hands. Every analysis reaches identical conclusions. Propulsion experts, life support engineers, radiation specialists, mission planners, psychologists. The verdict remains unanimous. Human missions to Uranus and back exceed capability by orders of magnitude. Not slightly difficult, not expensive, but achievable. Fundamentally impossible with any technology we have or will likely develop. The ice giant spins in outer darkness. Atmosphere howling at supersonic speeds. Radiation belts churning with deadly particles. Temperature colder than anywhere else in the solar system. Indifferent to human existence. Operating according to physics that predate humanity by billions of years. Those physics won't adjust, won't compromise, won't permit what mathematics forbids. Future generations will study Uranus remotely, through telescopes of increasing sophistication, via robotic probes of growing capability, using instruments we haven't invented yet. They'll understand the planet better than we do now. Map every atmospheric feature, analyze every moon, decode every mystery, all without sending humans into environments designed to kill them. This represents progress, evolution of exploration strategy. recognition that some destinations require observation rather than visitation, that scientific understanding doesn't demand human presence, that robots often achieve objectives better than fragile biology ever could. The boundary exists, clear, absolute, defined by mathematics and physics rather than choice. Uranus marks where human exploration stops, where remote observation begins, where we accept limitations built into the universe itself. The planet remains out there, magnificent, mysterious, forever beyond our reach. The first humans to reach Uranus will never return because they will never depart. The mission fails in the planning stage, where rocket equations expose impossibility, where radiation calculations show lethal doses, where life support requirements exceed any solution, where psychology predicts inevitable collapse, where every parameter screams the same message: don't go, can't go, won't survive. This conclusion isn't pessimistic, it's realistic, based on physics that don't negotiate, mathematics that don't compromise, biology that doesn't adapt to what it can't survive. The universe operates according to rules that exist whether humans acknowledge them or not. Those rules make Uranus unreachable by crude missions. Not today, not tomorrow, not with any foreseeable advancement. Humanity's reach extends far, but not infinitely. Some destinations remain forever beyond grasp. Uranus teaches this lesson with brutal clarity. The ice giant represents the edge of human capability, the boundary where ambition meets immovable reality, where physics wins every single time. Human missions to Uranus fail because physics demands it, because mathematics requires it, because biology can't survive it, because engineering can't solve it, because psychology can't endure it. The mission is impossible, completely, absolutely, permanently. The first humans to reach Uranus will never come back because they will never arrive. The universe has spoken, and its answer is no.